Okay, so hello everyone, and welcome to the 2021 edition of the Royal Tyrrell Museum Speaker Series. My name is Francois Terrier, and I'll be your host today. So today, the Royal Tyrrell Museum and its cooperating society are proud to present Mr. Jared Voris. Jared is a PhD student in the Department of Geoscience at the University of Calgary in Alberta, Canada. Jared is originally from Brevard, a small town in North Carolina in the southeastern US. After receiving his bachelor's degree in geology from Appalachian State University in Boone, North Carolina, Jared moved to Alberta to pursue a master's degree in the Department of Geoscience at the University of Calgary. For his thesis, Jared studied the anatomical changes associated with growth in the Tyrannosaur Gorgosaurus from Dinosaur Provincial Park in Alberta. After completing his master's thesis, Jared decided to stay at the U of C to pursue his PhD, for which he's studying growth and evolution in Tyrannosaurs, with a particular focus on the species found here in Alberta. Jared's primary research interests deal with understanding patterns of evolution and species diversification among apex predators like tyrannosaurs. He has conducted fieldwork in New Mexico, Utah, and of course here in Alberta. And just 1 year ago, Jared described and named the first tyrannosaur species from Canada in 50 years, the Reaper of Death Thanatothyristes, a discovery that received media coverage worldwide. So in today's talk, Jared will present an overview of the diversity of tyrannosaur species found in Alberta. So without further delay, it is with my great pleasure that I present Mr. Jared Voris. So Jared, the mic is yours.
All right, thank you very much. I guess everything's working, and if not, I'm sure I'll be notified of it here shortly. Okay, so my name is Jared Voris. I'm a PhD student here at the University of Calgary, where I've been kind of studying the various aspects of tyrannosaur biology for the last 5 or so years, particularly looking at their anatomy and how that can help us to understand their evolution and ecology. So today I'm going to be talking with you about some of the things that we've been able to learn about tyrannosaurs, particularly with those fossils that have come from right here in the province of Alberta. And so I'm going to try to touch on several different aspects of these tyrannosaurs, including the history of their significant discoveries, their ecology, as well as touching on something more directly associated with my research, which is discussing the anatomy, the species characteristics, life history, and also the evolution, and the origins of the different tyrannosaur species. But before we can actually dive into these topics, I think it's actually important to define what exactly is a tyrannosaur. And so I'm sure that for many, this immediately brings to mind T-Rex in Jurassic Park, or maybe even just images of these giant carnivorous predators. But in actuality, T-Rex is only one species of an entire group of dinosaurs known in the scientific literature as Tyrannosauroidea, or more generally as tyrannosaurs. And this includes any animal that falls on this red-colored branch here, or essentially any animal species that is more closely related to a T-Rex than to, say, a chicken or any other bird species. And tyrannosaurs are their own branch on the dinosaur family tree, and they're nestled right here between other well-known theropod dinosaur groups like Allosauroidea, which includes genera like Allosaurus and Giganotosaurus, and then also these more bird-like dinosaurs like ornithomimids, dromaeosaurs, and birds themselves. And these tyrannosaurs were a diverse group of carnivorous dinosaurs that have an incredibly long fossil record that spans nearly 100 million years, lasting from the Middle Jurassic all the way to the late Cretaceous. And if we put that amount of time in perspective, there's actually more time spanning between the earliest and latest known tyrannosaur species than there is actually between the latest tyrannosaur species and present day. But all these tyrannosaurs are actually united by a set of characteristics which we can use to distinguish them from some of these other meat-eating theropods like allosaurs and dromaeosaurs. And these include these things like having this uniquely wide snout, and this is quite easily seen in the bone that we call the premaxilla, that's written or marked here in red. And this sits at the very tip of the snout, and it's fitted with these very diagnostic incisor-like teeth in this kind of the side-by-side arrangement. And this is quite different than what we see in some of our other theropod dinosaurs, which usually have these narrower, more blade-like teeth in the premaxilla bone, with these teeth aligned more or less front to back. We also find that the nasal bones of Tyrannosaurs are also unique among other theropod dinosaurs, where most theropod species like Allosaurus here in the bottom right have these two separate nasal bones, one on the left side and one on the right. Tyrannosaurs actually had fused nasals, meaning they only had one nasal bone, and those left and right halves actually were fused into that single bone. And in some of our larger Tyrannosaurs in particular, the fact that the nasal was actually fused into that single bone actually helps in giving Tyrannosaurs those powerful bites that we've actually heard of them having, those powerful bone-crushing bites. And that they were able to better disperse some of the stress that built up while the animal bit down on bone or flesh than perhaps two separate nasal bones actually could. Now, the evolutionary history of Tyrannosaurs is actually quite interesting. While the most popular members of this group are the huge apex predator types like T-Rex, these giant species actually lived for a very short window of time, and for most of their evolutionary history, Tyrannosaurs were actually quite small, and instead of being the apex predators, were probably had an ecology more similar to modern-day jackals or coyotes. And these earlier Tyrannosaurs were actually quite bizarre and actually had an array of interesting features. They all had these relatively longer hind limbs and forelimbs, so they're more suited for running than some of our really large, bigger and more robust Tyrannosaurs. They also had the 3 fingers on their forelimbs or on their hands, which were again quite different than what we see with Tyrannosaurs, which generally have the 2 fingers. And some of them, like this genus here called Guanlong, had these really ornate head crests that likely served as some sort of display structure to help them attract mates. Other species like Dilong paradoxus here didn't have such tall crests, but did have these large air sacs right within this nasal bone, so in the same position as that large crest that we saw in Guanlong in the previous slide. And Dilong also is quite interesting in helping us to understand Tyrannosaur evolution because it also had these interesting feather-like structures that we can find on some of the preserved in some of the fossils from China. And so this suggests that at least in our earlier Tyrannosaurs, that they did indeed have feathers, perhaps losing them as some of our larger forms began to evolve in the late Cretaceous. And specifically with the late Cretaceous, that's actually when we start to see some of those larger Tyrannosaurs. So when we start to see some of the more familiar Tyrannosaur forms that had the giant body size, those small 2-fingered forelimbs, and those powerful bone-crushing jaws, which allowed them to fill that ecological niche of the larger apex predators. And it was the larger apex predator, or these larger Tyrannosaurs, that we actually find fossils of here in Alberta. And these larger forms are actually quite interesting, and they have a bunch of different features which kind of set them apart from the rest of their smaller cousins. And these include things like having this much deeper snouts, and this is one of those features that allow these larger Tyrannosaurs to have such powerful bone-crushing bite forces. We also see that the outer surfaces of the facial region of these Tyrannosaurs also have these roughened texture, and we actually see a wide range of these different types of patterning that gave this type of texturing depending on what species we're looking at. And so this is something that I'll actually touch on when we start to look at some of the individual species. In addition to this texturing, these larger Tyrannosaurs also had these small horns on the bones surrounding the eye cavity. And so this and the texturing likely played a role in some sort of display structures as well, essentially serving to help attract mates. So here in Alberta, we're incredibly lucky in that a large percentage of our land area, especially in the southwest areas of the province, have a lot of exposed rock layers that are rich in dinosaur and other vertebrate fossils. And this has led to Alberta being among the best places in the world for researching dinosaur paleontology. And this is especially true with regards to Tyrannosaurs, where we have this incredibly diverse Tyrannosaur fossil record here in the province, which has produced some exceptionally well-preserved specimens of multiple Tyrannosaur species. And in fact, much of what we know of Tyrannosaur biology, of the biology of these larger Tyrannosaur species, has come about thanks to discoveries that were made right here in Alberta. And so the vast majority of these fossils, again, come from the Badlands of the southern Alberta plains, where the bedrock is made up for the most part of a largely uninterrupted sequence of different rock layers that span the last 18 million years of the Cretaceous, dating from around 84 million to around 66 million years of age. And so we're going to explore some of the different Tyrannosaur species that we can actually find here in Alberta and what it is they've been able to tell us. But in order to do that, I'm going to do something that might seem a little bit backwards. Instead of moving forward in time from some of our earlier Tyrannosaurs to later, we're actually going to work our way backwards in time, starting at the very end of the Cretaceous, at the swan song of the reign of the dinosaurs. And so while I'm sure that many of you are already aware of the events that led to the extinction of the dinosaurs, we're going to get, for a short recap, around 66 million years ago, a colossal asteroid impacted the Earth in the location of what is present-day Yucatan Peninsula. And this event was catastrophic for most life forms living on Earth at the time, and actually led to the extinction of nearly 75% of all species on Earth. And this included the extinction of all non-bird dinosaurs, including the Tyrannosaurs. And the last living Tyrannosaur species in North America was actually none other than Tyrannosaurus Rex. And T-Rex actually lived here in North America between 67 and 66 million years ago. So actually a fairly short window of time of just about a million years, and potentially even just a little bit less than a million years. And this is much shorter than what we see in some of our other Tyrannosaurs that we'll be talking about later on. But Tyrannosaurus is the largest species of Tyrannosaur that we know of, and it also sits as one of the largest theropod dinosaurs ever discovered, and as well as one of the largest land predators to ever exist. At adult size, Tyrannosaurus was about the size of a school bus, measuring roughly 12 meters in length, and weighing anywhere between 8 and 14 metric tons, depending on what formula you use to calculate body mass. And compared to many other theropod dinosaurs, fossils of Tyrannosaurus are actually pretty common, with dozens of specimens having been found over the years. And this includes several fairly complete skeletons. And these specimens have been found all across Western North America, with the farthest northern occurrence is actually here in Alberta near the town of Huxley, with a range extending at least as far south as New Mexico and Texas, but potentially even as far south as Mexico itself. And because we have so many specimens of T-Rex, we've actually been able to learn a lot about the biology of the species. And in fact, there are more publications on T-Rex alone than there are for most any other animal species out there. And so we've been able to learn a lot about the biology of this animal over the years. And this includes studies looking at some very interesting studies looking at things like the creating digital reconstructions of Tyrannosaurus Rex brains using CT scans of the skulls. And we can actually use this even further to look at the sizes and shapes of the different lobes of the brain to actually determine how of the sensory capabilities of Tyrannosaurus Rex. And from these, we've actually been able to tell that T-Rex has a very acute sense of smell, as well as this superb hawk-like vision. We've also been able to find bite marks attributed to T-Rex found on fossil bones of Triceratops and Edmontosaurus, two prey species of Tyrannosaurus Rex. And this has led to studies looking at the bite forces of Tyrannosaurs or Tyrannosaurus Rex. And these studies estimate that T-Rex had a bite force of around 8,000 pounds, which is about the weight of two large cars. We even have some fossilized skin impressions of T-Rex, and this shows that T-Rex had this scaly reptilian-like skin, and perhaps didn't have the feathers that some of those earlier ancestors had, like Dilong that I was mentioning earlier. So here in Alberta, T-Rex fossils can be found in two different rock layers that we call the Scallard and Willow Creek formations. But despite the fact that there are quite a few fossils of Tyrannosaurus known, the vast majority of specimens of these T-Rex specimens are actually found in the US, and they predominantly come from the rock layers known as the Hell Creek Formation found in Montana and South Dakota. But here in Alberta, actually, we can find them in the, again, Scallard and Willow Creek formations, but those formations don't preserve fossils quite as well or as commonly as do similar aged rocks in the US. And despite that, there have been a few noteworthy specimens that have been discovered here over the years. And among the more famous of these specimens is the T-Rex commonly called Black Beauty. And this specimen was discovered back in 1980 by a group of young boys while they were fishing after school. And at first they were just finding these small black fragments of bone that were coming out of a hill. But when they showed them to their teacher realized that these shards had potential significance. And so they got into contact with the Royal Trail Museum staff, who launched an excavation of the site to find this incredibly well-preserved T-Rex specimen. And so Black Beauty has been quite important for helping paleontologists to understand T-Rex growth, as it actually represents a younger individual than some of our more famous T-Rex specimens like Sue at the Field Museum in Chicago or Scotty at the Royal Saskatchewan Museum. Another specimen of a larger T-Rex individual was found back in 1946, but it wasn't actually until 1981 that the site was more thoroughly excavated. And this specimen represents the most northern occurrence of a T-Rex skeleton that has been found to date. Again, being found near Huxley, Alberta. And this individual is represented by a partial skeleton, including the hips that you can see here on the right. But it also has a singular skull bone, one that we call the postorbital, marked here in red. And this bone forms the back margin for the eye cavity. So T-Rex had a lot of features which we can use to distinguish it from most other North American Tyrannosaurs, in addition to its larger body size. And these include features like having a fewer total number of teeth in their jaws. And this is largely attributed to T-Rex having these relatively larger teeth, which resulted in their jaws being unable to accommodate the higher tooth counts like we see in some of the other Tyrannosaur species. So it essentially is a trade-off between having these higher tooth counts versus larger teeth. T-Rex also didn't have this prominent horn on the top of the bone that sits in front of its eye socket. And this is the bone that we call the lacrimal. Instead, the top edge of this bone is actually quite flat in T-Rex. And this is due to a very large air sac inside this bone. In other Tyrannosaurs, its air sac isn't nearly as large, and it makes this horn much more prominent in those other species. We also see that the outer surface of the upper jaw of T-Rex was also ornamented with these really prominent ridges that separated these oval-shaped depressions just above the tooth row. And while we're not really sure what the function of these ridges was, it again may have been related to some sort of soft tissue display structure, or in other words, some kind of flashy feature that was used to help attract mates. Now, what's interesting specifically about these features is that while we can use them to distinguish Tyrannosaurus rex from other North American tyrannosaurs, we do see these same characteristics in these large Asian tyrannosaurs in species like Tarbosaurus from Mongolia and another tyrannosaur called Zhucheng tyrannus from China. And this tells us that T-Rex was actually likely not originally native to North America and was instead a derivative of an Asian tyrannosaur lineage that had likely immigrated into North America by crossing a land bridge that would have connected in what is present-day Alaska and Russia. And so, or just a little bit earlier than T-Rex, we have another Tyrannosaur species called Albertosaurus sarcophagus. And compared to T-Rex and many other Tyrannosaur species, Albertosaurus was actually a more lightly built animal with these relatively longer hind limbs and skulls that didn't have all the same features that was facilitated quite as high a bite force as some of these more robust Tyrannosaurs like T-Rex were capable of producing. But they still did have these incredible bone-crushing bites. They just weren't quite as powerful as some of these other ones had. And so Albertosaurus fossils are principally found in the rock unit known as the Horseshoe Canyon Formation and are actually quite abundant in the Drumheller Valley, but have been found as far north as Edmonton. And the layers that these animals come from date to around 71 to 69 million years of age, so just a few million years prior to the appearance of Tyrannosaurus in the fossil record. And Albertosaurus was actually among the first Tyrannosaurs that was discovered here in Western North America, with the holotype specimen, what is otherwise known as the namesake or the name-bearing specimen figured here on the left, being found just outside of Drumheller by Joseph B. Tyrrell while he was surveying the geology of Alberta back in 1884. And shortly thereafter, a second specimen was found by Thomas Cheston. You can see that individual is figured here on the right, and that individual was found back in 1889. And at the time, the discovery of these specimens were actually considered to be Western occurrences of an already named but smaller Tyrannosaur that could be found in New Jersey that was called Displetosaurus. And it wasn't until 1905 when the paleontologist by the name of Henry Fairfield Osborn of the American Museum of Natural History realized that these specimens represented an entirely different species, and he established them as a new genus and species, naming them Albertosaurus after Alberta, which had just been erected to province status that very same year. And one of the little facts that I find interesting is that Albertosaurus and Tyrannosaurus Rex were named in the same publication, with Tyrannosaurus Rex actually being named just 3 pages earlier. And because of the code that governs the naming of new species and groups, because the name Tyrannosaurus Rex actually came first in that document, it actually takes precedence over the naming of the entire group, which is why these animals are called tyrannosaurs. And so it's actually kind of funny to me that if Albertosaurus had been named just 3 pages earlier, we would instead be calling this entire group the Albertosaurs. And one of the more peculiar and important discoveries when it comes to Albertosaurus fossils are fossils that are found in what is called a bone bed in Dry Island Provincial Park. And this bone bed has yielded fossils of over a dozen Albertosaurus individuals that would have all been buried together during a very short window of time. And because we have so many individuals clustered in one area, this site has led to studies suggesting that there could have been some sort of grouping behavior within this species. But the unfortunate side of this is that we have no way of determining if this bone bed represents some kind of packing behavior, or if instead Albertosaurus were typically solitary animals, and this was just some sort of event where potentially there was just some sort of scavenging event where they were all scavenging on carcasses and all died in a potential flood event. But there are other fossils that provide evidence for some kind of social behavior in tyrannosaurs. One site in British Columbia that corresponds to ages similar to those of Albertosaurus fossils that can be found here in Alberta preserves footprints of 3 different tyrannosaur individuals walking in the same direction. And while we can't be sure what species made these tracks, this does provide some additional lines of evidence that there was at least some kind of social behavior that did occur in tyrannosaurs. So preceding Albertosaurus by a few million years, we have fossils of a similar tyrannosaur species called Gorgosaurus libratus. And this species is one of the more common tyrannosaurs that we find fossils of here in Alberta, with there having been dozens of skeletons discovered in the province since larger scale field excavations began in the early 1900s. And Gorgosaurus libratus is actually very closely related to and is very similar in many respects to Albertosaurus sarcophagus. And the two are actually even occasionally regarded as just 2 separate species of Albertosaurus. So Gorgosaurus fossils are found primarily in the Dinosaur Park Formation of southern Alberta, but are also found more rarely in the upper parts of the slightly older Old Man Formation. And these corresponds to an age of around 75.6 and 77 million years for this particular species. And so as with our T-Rex, there are actually a bunch of features that we can use to distinguish Gorgosaurus and Albertosaurus from other Tyrannosaurs that are found here in Alberta. And these include things like having these very prominent lacrimal horns, which are generally much more prominent and pointed and also more forward in position than what we see in some of our other Tyrannosaur species. We also have this hole that we call the upper, and this hole in the upper jaw that we call the Maxillary Fenestra. And in our Gorgosaurus and Albertosaurus, this hole is much smaller than in some of our other Albertan Tyrannosaurs, like Displetosaurus and T-Rex or this Displetosaurus, like you can see here in the bottom right corner. We also find that the nasal bone that sits right along the top of the snout of Gorgosaurus and Albertosaurus are also shaped differently than some of our other Tyrannosaur species that we have here in Alberta. For example, in Gorgosaurus, the width of the nasal is largely consistent as we move backwards along the length of the bone, where in our other Tyrannosaurs like Displetosaurus and T-Rex, we actually see that the bone actually begins to narrow as we get closer to that back end. We also find that at the front of the nasal bone, that Gorgosaurus and Albertosaurus have these three separate points with two on either side and one on the midline of the bone. And this contrasts what we see in our other Tyrannosaurs, which don't usually have that middle point and instead only have those two side points. And so with Gorgosaurus fossils being some of the more common Tyrannosaur fossils that we found here in the province of Alberta, we've actually been able to learn a lot about the biology and life history of Tyrannosaurs through this particular species. And particularly, we've been able to learn a lot about Tyrannosaur growth. And in fact, Gorgosaurus is one of the few Tyrannosaurs that we actually have a really complete growth series for that includes fossils of some smaller and younger juvenile individuals all the way through these larger adult animals. And recently, in fact, this growth series has been expanded thanks to discoveries of two exceptionally well-preserved juvenile Gorgosaurus specimens at the Royal Trail Museum, or by the Royal Trail Museum. And these two individuals represent some of the smallest articulated Tyrannosaur skeletons that have been found all over North America. And so these two specimens in particular demonstrate just how significant the changes that Tyrannosaurs underwent, or the changes that Tyrannosaurs actually underwent as they matured. And so what we can actually see when we compare some of these younger and smaller individuals of Gorgosaurus to the older and more mature counterparts is that these younger individuals had these incredibly long hind limbs relative to the rest of their body. Their skulls and skeletons were overall much more lightly built, and they also had these narrow blade-like teeth that would have been much more suited for cutting through flesh rather than crushing bone. And as they got older, the Tyrannosaurs bulked up significantly. Their hind limbs became shorter with respect to their overall body size. Their skulls and skeletons became much more robust, and their jaws became much more powerfully built and were fitted with these very large conical teeth. And it was these features that actually helped to facilitate some of those incredible bone-crushing bites that Tyrannosaurs are famous for. And such extreme differences between the overall builds of these juvenile and adult Tyrannosaurs suggest that these different age groups likely had different ecological roles. These fleeter-footed juveniles were likely preying on smaller and faster prey such as oviraptorid or ornithomimid or ostrich-mimic dinosaurs, where these adults were preying on slower and heavier prey like ceratopsids and hadrosaurs. And so this highlights a very interesting ecological dynamic where Tyrannosaurs were actually dominating multiple predator roles throughout their lifetime, including both apex predator and lower tier predator roles. And this is quite different than what we see in other dinosaur-dominated ecosystems, as well as some of our modern ecosystems where different species occupy different ecological roles. For example, if we compare this to modern African savanna, juvenile Tyrannosaurs would actually be occupying a role similar to what modern-day cheetahs and leopards are, where adults were occupying the role that the apex predator role like lions occupy. Now, interestingly, Gorgosaurus is actually not the only Tyrannosaur that we can find here in Alberta from this time period, from this dinosaur park and Old Man Formation. We can also find fossils of another Tyrannosaur species called Displetosaurus, Displetosaurus turosus, in these same rock layers. And so Displetosaurus actually, again, comes from has this very interesting skull shape, and it comes from the same time period. So it suggests that there's some very interesting ecological dynamic that's going on between Gorgosaurus and Displetosaurus that hasn't really been fully explored yet. But what would actually have ended up being named as the holotype specimen of Displetosaurus was actually discovered back in 1921. But it was largely considered to be a specimen of Gorgosaurus for nearly 50 years until 1970, when paleontologist Dale Russell realized that they were actually something completely different. And since then, we've actually discovered several additional specimens of this genus, which includes some very well-preserved specimens like the exploded Tyrannosaur skull that's currently on display at the Royal Trail Museum. And it's also been discovered that there are actually two species of Displetosaurus that were separated by a little bit of time, where Displetosaurus trosis comes from the Old Man and Dinosaur Park formations dating to around 77 to around 75.6 million years of age. And the younger Displetosaurus horneri can be found in the Two Medicine Formation of Montana, which dates to around 75.1 or to 74.4 million years of age. So a little bit of a time difference there. And one interesting note is, again, that these two individuals, or these two Tyrannosaurs, Gorgosaurus and Displetosaurus, are sharing that dinosaur park ecosystem. And so but when we compare the actual abundances of these fossils, we actually find that Gorgosaurus actually is about 2 times as abundant in the dinosaur park ecosystem as fossils as those identifiable to Displetosaurus. But interestingly, we actually see the inverse to be the case as we move further south into the similar aged rocks of Montana. And so what this might suggest is that there's some sort of geographic separation between these two groups, where Gorgosaurus and Albertosaurus represented perhaps a more northern lineage, and Displetosaurus maybe represented a slightly more southern lineage. And this is just actually a small aspect of this Tyrannosaur biology from the similar time range. We actually see further geographic separation as we move further south into places like Utah and New Mexico, where we find that there are entirely different Tyrannosaur species there as well. And in fact, we don't find any of these species here in Alberta. And this suggests that there were essentially different Tyrannosaur zones, which can principally be broken up into a northern zone here in Alberta and Montana, and perhaps a southern zone in Utah and New Mexico, and maybe even further south into Texas as well. So Displetosaurus can be distinguished from other Tyrannosaurs by a wide range of features in the upper jaws, as well as in some of the other ornamental bones. In the upper jaws, we actually see that there are these deep branching channels that meander across the outer surface of this bone, which gives the surface of this bone an almost scale-like texturing. And we don't see anything like this in some of our other Tyrannosaur species like Gorgosaurus and Albertosaurus. We also find that in addition to the horns in front of the eye, Displetosaurus also has these very large horns on the bone that sits behind the eye, on the bone that we call the postorbital. And these are relatively larger than what we see in similar structures of any other Tyrannosaur species. And Displetosaurus also had this much more oval-shaped orbit, which is what we call, or the orbit, which is the cavity which would have held the eyeball in life. And this is much more oval-shaped in contrast with what we see in other Tyrannosaurs, which have this more comma or apostrophe-shaped eye cavity. Now, other features of Displetosaurus can be used to help us to piece together where this particular species falls in terms of our Tyrannosaur family tree, or in other words, what it's more closely related to. And in particular, Displetosaurus has a more robust skull, thicker teeth, and a heavier body frame than what we see in similar sized individuals of Gorgosaurus and Albertosaurus. And so these are similar to what we see in T-Rex and Tarbosaurus and other related species. And so this tells us that Displetosaurus was probably more closely related to Tyrannosaurus and Tarbosaurus than perhaps were Gorgosaurus or Albertosaurus. Now, as we move further down in our rock layers, we find that there isn't nearly as much diagnostic fossil material that's preserved when compared to the fossil-rich Dinosaur Park and Horseshoe Canyon formations, but we have found some fossils in the rock layers known as the foremost formations, such as the Pachycephalosaur colepiocephaly and the Ceratopsis xenoceratops. But until recently, we haven't had much of a record of Tyrannosaurs from this unit, other than a few isolated teeth, which alone unfortunately can't help us in determining exactly what species they belong to. But around 2010, a friend of mine named John DeGroot found skull bones of a Tyrannosaur from his formation near his ranch while he was walking along the Bow River with his family. And more recently, we realized that these particular skull bones had features that we don't see in any other Tyrannosaur species from here in Alberta. And so because of this, we were able to determine that this actually represented a new species of Tyrannosaur that we called Thanatothrustes degrutorum, naming it after John and his family. So Thanatothrustes is the oldest Tyrannosaur that we've been able to find diagnostic fossil material of here in Alberta, again coming from that time window of around 79.5 million years of age, making it nearly 2.5 million years older than the next occurring species of Displetosaurus and Gorgosaurus. But what's particularly interesting about this species is that when compared the bones of Thanatothrustes to those of other Tyrannosaur species, we actually find that it exhibits similarities of two different lineages, these more T-Rex-like species and these more Displetosaurus-like species. For example, if we look at the outer surface of the upper jaw of Thanatothrustes, we see that it has these prominent ridges, which, if you recall, are very similar to what we see in Tyrannosaurus and Tarbosaurus. But at the same time, we also see that it has these deep branching grooves and scale-like patterning of bone like we see in Displetosaurus. We also see that the jugal or the cheekbone of Thanatophrystes is actually quite similar to what we see in the Asian Tarbosaurus, and that the part of the bone that forms the bottom of the eye socket is thickened and is much more rounded in cross-section than in Displetosaurus specifically. And it also lacks the thin blade-like edge of bone like Displetosaurus has, or thin blade-like upper edge of this bone, or the same margin that Displetosaurus has. And so looking at a zoomed-in version of our Tyrannosaur family tree, we see that Displetosaurus and Tyrannosaurus are quite similar, but because the Thanatophrystes has characteristics of both these Displetosaurus and Tyrannosaurus-like species, that it actually suggests that this species actually may occur very close to the evolutionary split between these two separate lineages. And this actually corresponds well with what previous studies have estimated the timing of this split between Displetosaurus and T-Rex to being around 79 million years of age. So this again actually comes from that time period during that split. So this might be a very significant animal that in future discoveries will help us to further understand. But we can actually use it currently to try and piece together some of the geography of Tyrannosaurs and their evolutionary history. So what this actually might suggest is that around 80 to 79 million years ago, a Tyrannosaur very similar to Thanatophrystes or group form either had a very large range that spanned across both North America and Asia, or it alternatively originated here in North America and crossed that land bridge into Asia around that 80 million year window. And over time, these North American and Asian populations became isolated from one another, resulting in entirely different species arising in these two different areas, with genera like Displetosaurus arising here in Alberta and Zhucheng Tyrannosaurus and Tarbosaurus arising in Asia. Then, as I mentioned earlier, at around 67 million years ago, we see that Tyrannosaurus Rex actually coming back to North America, then going on to dominate much of Western North America shortly before the extinction that wiped out the dinosaurs. So Thanatophrystes provided us with this very interesting window into the origins and the biology of these two separate lineages, and this is something that the discovery of additional specimens will undoubtedly help to clarify further. Now, unfortunately, as we start to look further back in time and further down in the rock layers, we encounter a little bit of a problem. From around 80 to 100 million years ago, we have this huge global gap in our dinosaur fossil record where there just aren't that many rocks that preserve fossils, and there are even fewer that preserve fossils very well. So we don't really know much about the dinosaurs that actually lived during this time period, and this actually includes the Tyrannosaurs. And so what's upsetting is that somewhere within this gap, we have this critical moment in the evolutionary history of Tyrannosaurs where we see the transition from these smaller body species to these giant apex predator forms that we're more familiar with. But paleontologists are beginning to make discoveries that are helping to piece together and narrow this gap. And in fact, there have been a few species discovered within the last 5 years, which have especially helped us to understand Tyrannosaurs from this previously missing time window. And these include species like Moros intrepidus, known from a partial but rather well-preserved leg from the Cedar Mountain Formation in Utah. And this is dated to around 96.5 million years of age. We also have Suskityrannus hazelae, known from skeletons of two separate individuals from the Moreno Hill Formation in Arizona, dated to around 92 million years of age. And we also have Timurlengia uotica, which is known from various bones from several individuals found in the Besekti Formation of Uzbekistan, which is dated to around between 92 and 90 million years of age. And all of these different Tyrannosaur species have some pretty advanced Tyrannosaur characteristics that we see in some of our larger Tyrannosaur species. But these species are still quite small in their body size. So even with these newer discoveries and the reduction in the size of this gap in the Tyrannosaur fossil record, we're still lacking in fossils from that critical time period in that evolutionary history of Tyrannosaurs, or that ascent into that large body size, the powerful jaws, and the apex predator ecology that Tyrannosaurs are famous for having. But here in Alberta, there is one rock formation from within this 10 million year gap that does rarely produce dinosaur fossils. And this is the Milk River Formation found at the very southernmost edge of Alberta. And this rock formation dates to around 4 million years before Thanatophrystes, or around 84 million years of age. And this corresponds to a time period called the Santonian Age of the Cretaceous. And this formation has actually produced a few isolated Tyrannosaur teeth. And while we don't know much about the Tyrannosaur that these teeth came from, or what species they actually were, what we can tell from the size and shape of its teeth is that they would have been from a larger apex predator like the other Tyrannosaurs that we've already talked about. And this is very important because in addition to being the oldest Tyrannosaur that we have fossils of here in Alberta, these teeth come from some of the earliest large-bodied Tyrannosaurs that we have fossils of from anywhere around the world. And so they have great potential for helping us to further piece together the evolution and even the origins of some of those hallmark features that allowed Tyrannosaurs to ascend into that apex predator lifestyle. And beyond the Milk River Formation, there are other poorly explored and potentially fossil-bearing rock layers here in Alberta that correspond to some of these time periods to just before Tyrannosaurs had evolved into that apex predator ecology. And so there's a possibility that there are fossils of some of these more smaller, more primitive Tyrannosaur species right here in Alberta that just haven't been found yet. And this is something that more paleontological work in these underexplored areas will likely help to fix. But one of the problems that we paleontologists frequently have is that many of these places are quite remote, and we unfortunately can't devote as much time to looking for new fossil localities in some of these areas as we'd often like to. And I think this is where the public is actually better poised to make some of these groundbreaking discoveries more often than paleontologists are. So if you find yourself out in some of these potential fossil-bearing areas, keep an eye out for fossils, as they could represent the next groundbreaking paleontological discovery. But I think it's important to not diminish the significance of continued paleontological work in places like Dinosaur Provincial Park, as there's still much that we do not know about the biology of even our more common and well-known Tyrannosaur species like Gorgosaurus and T-Rex, and things that we're still discovering things about these animals to this very day. And so I think this highlights that despite being perhaps the most famous of all dinosaur groups, that there's still a lot that we can learn about Tyrannosaurs. And I think that Alberta in particular has only just really started to answer some of those really big questions that we have about Tyrannosaurs. And I think it's going to continue to be an epicenter for groundbreaking discoveries about Tyrannosaur biology and lifestyle. And so with that, I'd like to thank my funding sources, as well as several people that I'd like to personally thank for their continued support in these various projects. And I'd also like to thank everybody for tuning into this talk, and I hope it's been fun, and I hope that you all learned something interesting about Tyrannosaurs that you maybe didn't know before. And with that, I guess I can take any questions.
Okay, well, thank you very much, Jared, for a great presentation. I see that we have lots of questions from the public. And before we move on to the questions, I'd just like to invite you, if you have questions for Jared, please type them below in the little Q&A box, and we'll go through them. And before some of you may have to leave for lunch, I'd just like to announce the talk for next week. We'll have Miss Nisaiba Raja Shob from the Friedrich Alexander University in Erlangen, Nuremberg in Germany, who will give a talk entitled Illicit Fossils, the Ethical Dilemma in Protecting the World's Natural History. So I invite you to come to watch this talk next week. So I can see that there's a few questions that have been coming in. So Jared, if you're ready, I'm gonna read you a few of those questions.
Absolutely.
Okay.
Take them.
So first question was about the nasal bones that you mentioned were fused in Tyrannosaurs. Mm-hmm. So the question from Sarah is, were the nasal bones fused after hatching, or did they grow that way to begin with?
So this is a question that we're not really quite sure of. We have the youngest individuals of Tyrannosaurs that we have come from a Tyrannosaur specimen of Tarbosaurus that had a skull length of around 30 centimeters. So it was actually a fairly small individual. And I know that's still about dog-sized skull, but the nasals were already fused in that individual. So it at least suggests that they were fusing very early in ontogeny, or very early in life. As for if they were fused immediately upon hatching, we're not quite sure yet. That's something that's going to have to be that would be something that would have to be addressed once we find a Tyrannosaur nest, or a Tyrannosaur embryos, or Tyrannosaur hatchlings, which has still not happened, but fingers crossed that happens in the near future.
Awesome. We have a few questions from Sarah, actually, so I'll just keep going. Okay. She was asking about the patch of fossilized skin you showed. She's asking if we know from what part of the body that the skin for Tyrannosaurs is coming from, if we know where it's what body part it's from.
We've got skin patches from various Tyrannosaur species that come from kind of all over the body. They're never very large patches, so we don't have a Tyrannosaur mummy yet. That's another thing that needs to be found. So if anybody's out there digging, look for that. But we have patches from all over the body. I know that there are patches that come from the torso area, from right along the back. There are some Albertosaurus ones that come from the tail area. There are other patches that are coming from around the neck area, and we also have footprint fossils that give kind of impressions of around the foot area. So they're smaller, so they're not giant, huge patches of these skin impressions, but there are quite a bit from all over around the body.
Question about the lacrimal that you said was enlarged in T-Rex. So Sarah's asking if the reduced lacrimal size, I guess, of the horn could be reduced to vision, to better vision in T-Rex.
Potentially. The thing is, though, is that the lacrimal horn, even in some of our other Tyrannosaur species, the lacrimal horn really wouldn't be in the way. We can determine kind of the orientation that Tyrannosaurs held their head by looking at CT scans of the inside of their skulls. And then we can look at basically the inner ear structures. And there's a loop in the inner ear that will tell you, that kind of gives you what is generally called the resting head orientation. So where what their head orientation was when they were just resting. And usually that holds it pretty much lateral. So their nose would have been pointing pretty much straight forward. And in those cases, usually the lacrimal horns are pointed upwards and are situated on the top of the skull. So even in some of our Tyrannosaurs that did have those horns, they probably weren't obscuring their vision all that much. In Tyrannosaurus Rex itself, it seems that the absence of the horns are predominantly due to just an extreme amount of inflation of the bone by that air chamber, that sinus chamber inside of that bone.
One more question from Sarah. What can you say about the size of the smaller maxillary fenestra? You shown that thing was smaller in Gorgosaurus or Albertosaurines than in Tyrannosaurines. So what could be a possible function maybe for the smaller maxillary fenestra?
Well, so the smaller maxillary fenestra seems to kind of be the ancestral morphology or the ancestral characteristic in Albertosaurians. So it's also seen in some of our more basal Tyrannosaurs. So it seems to be just retaining that smaller size. In our larger Tyrannosaurs, the fact that we have the larger maxillary fenestra might actually be some sort of method of changing the shape and position of the sinus that actually would have been situated along that upper jaw area. It potentially would also be related to a greater inflation of that sinus as well. So the larger hole might have been giving better airflow between the inside and the outside parts of the bone.
We have a question from Joanna. Hi, Joanna. Do you feel that T-Rex and other later and larger Tyrannosaurs were completely featherless? Or do you think that they retained a few feathers on some body parts?
So that's a big question. We really don't know is one of the things that I kind of sit on the fence on this. So like there could be feathers and there might not be. Currently, we don't have any evidence that there are feathers in some of our larger Tyrannosaurs. But that's not to say that they can't be there. For the most part, elephants are hairless, but they still have fur, or they still have a little bit of hair on their bodies, where mammoths had lots of fur or whatever. And their ancestors also had large amounts of fur as well. It does seem that for the most part that Tyrannosaurs seem to have lost most of their feathers if they had any at all. And if they did have feathers, there's probably going to be potentially on the tail area or on the top of the neck, potentially places like that. But again, we really don't have any evidence of feathers in those animals yet.
Question from Robert. What biomechanical tests have been done with Tyrannosaurid forearms for showing how strong they are and how much they could lift?
There's been a couple of studies. I think Kenneth Carpenter actually has done a couple of them to look at like the range of motion. But the thing that if I recall correct, it's been a while since I've read that paper, but they didn't have all that much motion in their forearms. They had a very low angle, but they were heavily muscular. But I think it's important to kind of to say here that the reduced forearms in Tyrannosaurs are not unique to Tyrannosaurs. It seems to happen that once these larger theropod meat eaters got large, that a lot of times we did see them reducing the size of their arms. So in Abelisaurs like Carnotaurus and Majungasaurus, and also in our Carcharodontosaurs like Giganotosaurus and Carcharodontosaurus itself, we're seeing these very small arms. So it seems to be that as they got bigger, these larger meat-eating predators just didn't need their arms as much as their arms weren't playing as much of a role in their lifestyle as was their heads. And so potentially it's just they're reducing their arm size because it's just not as useful to retain large arms and waste those resources on features that you're not really using all that much.
We have a question from Darren. When T-Rex first came to North America, there must have been native Tyrannosaurs here already. Did T-Rex outcompete the Albertosaurs? Are there any occurrences of T-Rex and Albertosaur-like species found together in North America?
As far as we're aware, no. There's, of course, the argument that of Nanotyrannus, but Nanotyrannus has pretty effectively been shown to not, if it's a valid animal, which I'm of the opinion that it's not, it would not have been an Albertosaur. It would have been a derived Tyrannosaurian very close to T-Rex. But before T-Rex actually got here, the last occurring Tyrannosaur that we have a fossil record for was Albertosaurus sarcophagus, and those seem to go extinct around 69 million years ago. Or we don't have a fossil record of them after around 69, maybe 68 million years of age. So there's a little bit of a gap between Albertosaurus and T-Rex, and whether or not that's a stratigraph or just a gap because we don't have fossils from there, we don't really know. So we really can't say yet. We don't have any overlap in their fossils. It could have been that T-Rex actually arriving in North America actually displaced Albertosaurus or other Tyrannosaurs and potentially led to their extinction. But that's something where we'd have to get better sampling of the periods that actually come between, like the Horseshoe Canyon Formation and the Hell Creek Formation, or that time period around 68 million years of age.
I have a question from Nicholas. I think it's somewhat related to what you mentioned earlier about skin impression. How sure are we that giant tyrannosaurs had feathers at adult size? Is there skin imprints that could help provide some answers?
Yeah, kind of going back to that, the skin impressions current skin impressions that we have of Tyrannosaurs don't show feathers on these larger species, not like what we see in Dialong and some of our weirdly large or enlarged basal Tyrannosaurs, something like Tyrannus, which does have feathers, but that's an entirely different lineage of basal Tyrannosaur. But currently, we don't have any evidence of feathers in some of our larger Tyrannosaurs, like Albertosaurus, Gorgosaurus, and T-Rex, or Tarbosaurus as well. And it's kind of one of those questions that would really need better sampling of those skin impressions, and also potentially even a Tyrannosaur mummy could help to address that question. But currently, we don't have any evidence of feathers in some of those really large late Cretaceous Tyrannosaurs.
We have a question for Mark. Is it possible that Tyrannosaurs could have given, basically delivered infectious bites similar to what Komodo dragons did in order possibly to avoid dangerous prey like the ceratopsians, the horned dinosaurs?
I mean, it's always possible. I imagine that being bit by most any animal and having an open wound would be grounds for opening it up to an infection. Plus, saliva is not especially in a saliva of an apex predator, is not the cleanest of substances. So having that in an open wound would not be good to have going on. As for if it's specifically tailored its mouth to having an infectious bite, I don't really know if there's any way that we can really test that, unfortunately. There are some weird pathologies that are found on Tyrannosaur jaws that have been suggested to be related to bite marks, but I don't know if that's really held up much to more recent work.
I have a question from Alexandra. She's asking, what are the age markers that you use to indicate the age of the dinosaurs at the time of their death?
Here in Alberta, we were actually really lucky that a lot of the age markers that we actually have are these ash beds, so layers of ash that were laid down by volcanic eruptions. And these ash beds contain minerals that we can actually radiometrically date using radioactive decay methods, right? So like half-life, if you know anything like that. And these can give us very clear age dates on the rocks. And so if we find fossils in between two ash beds, so one ash bed dating to around 74 million years and another dating to around 76 million years, we can be sure, or we can be fairly confident that the animal that's coming between those rock layers is somewhere between 74 and 76 million years of age. And we can also use layer principles of stratigraphy to kind of look for laterally continuous beds. So if we find similar layers in the north that we have, or in Alberta that are that have ash layers, and then maybe in Montana we find a similar rock layer or some rock layer of the same type, we can potentially date those using similar methods if we don't have radiometric capabilities in those layers down in the south.
I have another question from Tom. Where did the first dinosaurs appear, or where did they originate?
This is a question that's not really pertaining to my research, so to speak. I'm not really as well versed on the actual origins of dinosaurs. As far as I'm aware, though, if I recall correctly, the most recent hypothesis suggests that dinosaurs actually originated in the Eurasian African landmass of what would have been Pangaea. So across the Atlantic Ocean currently, not over here in what would have been Laurentia or the North American kind of landmass, North American, South American landmass.
Nice. A question from Dimitri. What do you think about the lip theory? Did tyrannosaurs have protruding teeth, or were they hidden under lips?
I don't really have much of an opinion on this one, so to speak. So the idea here, the theory is that some of our tyrannosaurs they had more of like a crocodile kind of face where their teeth were exposed to the air. So they had like that very toothy grin already. And then there are some people who suggest that tyrannosaurs actually had lips to cover them. I'm kind of the idea more so that they probably did have lips, but there has been other work that has suggested that they might not have. And so it's kind of going to probably require, again, a tyrannosaur mummy to kind of confirm or reject confirm which of those is actually the correct hypothesis.
Nice. A question from Cam. Just curious, has there been many tyrannosaurs discovered in Alaska? If so, are they similar to the Alberta specimens or species?
There is one tyrannosaur known from Alaska currently, Nanuqsaurus hoglundi. And that is known from I know that there's other material of it, but that one particular has the holotype, or the namesake specimen is a partial skull. And from what we can tell currently, it suggests the characteristics of that partial skull, of the bones that they have of that, it suggests that it actually comes from an animal that is somewhere between Displetosaurus and Gorgosaurus, or Displetosaurus, Gorgosaurus, and Albertosaurus, somewhere in between those major lineages. So it would have probably been a Tyrannosaurian in that regard.
We've got a question about early tyrannosaurs. When early tyrannosaurs were still very small predators, what were the apex predators in those ecosystems?
Yeah, so when tyrannosaurs were the smaller, like what we call mesopredators, so like those jackal and coyote type predators, at the time, most ecosystems that tyrannosaurs lived in were dominated by these large carcharodontosaurs, or these large allosaurs, right? And so it kind of varies depending on what time period you're on. If you're in the early Cretaceous, they're probably these carcharodontosaurs, and then if you're in the Jurassic, then we're more likely to be like allosaurs or stuff like that. There have been a few hypotheses that actually suggest that tyrannosaurs might have been much more earlier on, where maybe more widespread in their distribution, potentially even being found in South America. And if that were the case, that potentially could even been co-occurring alongside some abelisaurs like Carnotaurus. Maybe not Carnotaurus itself, but something like within that abelisaur lineage.
I have a question about the ridges on the jaws that you mentioned for, I guess, T-Rex and Displetosaurus. Do the ridges on the jaws suggest very vascular tissue?
We're not really sure, but what I think it does suggest is that there's some sort of, I guess, scaling texture or scaling differences. There's maybe some differences in the morphology of the scales that we would have seen in like Displetosaurus, where Displetosaurus has those really deep grooves that we see, and T-Rex and Thanathosaurus have those very prominent ridges. It might indicate that the different types of texturing that we're seeing in the upper jaw relate to some differences in the scale morphology during what would have been in life. And that's, again, something that I would really like to see a mummy or skin impressions of it on the upper jaw. The answer for everything is to find a Tyrannosaur mummy, I guess.
Yeah, that would be great.
Everybody get on that, please.
Yeah, a Tyrannosaur mummy covered with feathers, sitting on top of a nest, and with embryos inside the eggs.
Exactly. The holy grail of Tyrannosaur paleontology.
Okay, we have another question from Mark. Given that the later tyrannosaurs were large and had well-developed olfactory bulbs, would they have obtained most of their food by driving small predators of their prey, which they detected by scent? Or I guess would the alternative question is, would they have been more active predators rather than scavengers?
I think this is just kind of like the idea of like, oh, well, like do Tyrannosaurs scavengers or predators? The kind of the short answer is that in modern ecosystems, most predators are opportunistic. Even lions, which are generally shown to be like these always hunting, or these predators that hunt their prey, will, when they come across a carcass or a decaying carcass, even they'll consume that. So these predators are always opportunistic. They're not really that picky when it comes to what food they're consuming. But I think it's also important to note that there are studies looking at the brain, so not just the olfactory, not just the olfactory lobes, but looking at some of the optic capabilities, so the visual acuity of Tyrannosaurs has suggested that the Tyrannosaurs had very superb vision, and potentially even on being able to see things like at the same level that potentially even hawks could see. So very strong vision. So they very well could have just been both really good with sense of smell and vision. So they could have been hunting or scavenging both. And they probably likely were. They were probably doing whatever they could to survive.
Question from Brent. Why can't we use teeth to identify different species of tyrannosaurs?
The main issue is that teeth change a lot with ontogeny, or with growth. So if we look at our juvenile Gorgosaurus specimens, the teeth are very narrow. And this is something that we actually see with like what are oftentimes referred to as nanotyrannus teeth. Those teeth are very narrow. So it seems that early on in their growth series that these Tyrannosaur teeth are very slender and very narrow, much more suited for cutting through flesh than for crushing through bone. But as they got older, they started to slowly widen and get thicker and become much more what we call encrasite, or these thick spike-like teeth that were used for crushing bone. And so because they're so variable, with ontogeny or with growth, it's really difficult to actually determine what Tyrannosaur tooth actually, or what teeth a Tyrannosaur's, or what Tyrannosaur an isolated tooth might come from. And to that point, while like say Displetosaurus has these wider teeth than Gorgosaurus, the problem would be is you'd have to have a large adult Gorgosaurus and a large adult Displetosaurus to really be able to say one way or another. And even still, I would be very hesitant to kind of say that an isolated tooth was Displetosaurus or Gorgosaurus, to be very solid on one way or another if I were to find one in like the dinosaur park ecosystem.
Plus, on top of that, since they constantly replace their teeth, at one point your giant adult Displetosaurus would still have smaller teeth because they're not yet fully grown.
So. Exactly. So there'll be a lot of overlap in terms of their morphologies with other species. So it's really difficult to say one way or another as to what species an isolated tooth might come from. Unless there's only one species in that formation, like in places like T-Rex, then that would be, you can be pretty confident that it's probably a T-Rex.
Question from Arian. Could the weirdly shaped orbits of T-Rex that are like H-shaped, what could be their purpose? Why would the orbit have that shape?
I think that the weirdly shaped orbits of like T-Rex compared to our other Tyrannosaurs, if we look at like Gorgosaurus or something like that, you'll actually see that our larger Gorgosaurus also have a fairly similar shape to T-Rex. It's just the orbits aren't nearly as tall or deep. The one thing about T-Rex, though, is that T-Rex is significantly larger than most other Tyrannosaur species. And so I think that what's going on here is that even in all of our Tyrannosaurs, the eyes aren't really changing in size all that much. And so when you get a large animal like T-Rex, it has a similar sized eye to something like Gorgosaurus and to a Gorgosaurus and Displetosaurus. So the orbit just gets long, seems to look more stretched and has a smaller, and relative to the size of the skull, looks to have a much smaller eye cavity. But in reality, it's just because it's a larger animal. And that's something that we see with ontogeny. If you compare like the orbit size or the eyeball bearing part of that orbit size between a juvenile Gorgosaurus and an adult Gorgosaurus, they're almost the same size, but they change in shape because the animal's getting larger.
Question from Gary. How does Scotty the T-Rex fit on the record being further east near East End, Saskatchewan? How many complete specimens have been found of T-Rex?
Ooh, there's been a lot. Dr. Thomas Carr is actually probably the biggest expert on T-Rex itself. he's done a lot of really good work on that species in particular. But T-Rex comes from all over. It seems like it has all across North America, from Huxley all the way again down to Mexico. I'm not really sure what the furthest easterly specimen is. And I guess I'm also not really sure what the furthest west specimen is. Probably maybe something in South Dakota or North Dakota, those sorts of areas on the eastern side. But they had a very large range. And so Scotty has helped us to better understand the maximum size ranges of T-Rex and like how big they could have gotten. But I'm not really 100% sure what it's told us regarding the geography itself. But there, as to the specimen number question, there are tons of Tyrannosaurus specimens found. I don't know the exact number, but I know that there are probably more T-Rex specimens than there are for most any other Tyrannosaur species known. But they're mostly all large adult individuals, or mostly close in that really large adult category.
Question about the Tyrannosaur track site that you mentioned, discovered in BC by Rich McRae. Were they all adult-sized tracks, or were there different-sized individuals? Could this possibly further indicate some social behavior in tyrannosaurs?
Yes, I think that they were all large adult individuals, and it's also really interesting to kind of note that the study, when they found them, actually, the deviation from like which direction they were going, they were all like kind of almost identically parallel, heading in almost the exact same angle. So that did suggest they were all walking in the same direction. And I think that's one of our biggest lines of evidence for some sort of social behavior in Tyrannosaurs currently. That, I guess, and also like the fact that we find bite marks on a lot of Tyrannosaur specimens. So suggesting that they're interacting with one another. As to what that means, if they're hunting together or anything else, we really can't say. And that's one of the problems with paleontology, is we're not preserving. It's very rare that we get behavior like hunting preserved in the fossil record, and it takes an exceptional case of like the fighting dinosaurs in Mongolia to really show that.
Question from Mark: given that it appears that juvenile and adult tyrannosaurs filled up all the predatory niche in an ecosystem, would this mitigate against them being social animals as subadults and adult animals, as they would have? As a subadult and as adult animals would, as you stated, since they would have hunted different prey.
Yeah, so I guess that's one of the questions of like parental care, and I guess it could be used as evidence to suggest that maybe juvenile tyrannosaurs were hunting on their own. It's really difficult to say, I guess, and we'd have to find some exceptional specimens in order to really answer that question as well. And again, that's also another question that we maybe not even can't really answer unless we found something truly exceptional. What's interesting, I think, is that what's interesting about the kind of the disparity between our juvenile and adult forms is that it does highlight that very interesting ecological dynamic, which is really different from most other dinosaur-dominated ecosystems. Like if you look in the Morrison Formation in the U.S., there are large predators like Allosaurus and Torvosaurus taking on the apex predator roles, but at the same time you have smaller theropod species taking on the mesopredator role. So entirely different species, things like Stoxosaurus and Ceratosaurus, even, it's like slightly smaller than those other ones. So you have different tiers of predators that are being occupied by different species of theropods. In Tyrannosaur dominated ecosystems, though, we don't get that. We have Tyrannosaurs dominating from their juvenile stage. We have them taking on that mesopredator role, so that jackal, hot coyote type role, all the way up to them being the apex predator, where they're taking on things like ceratopsids and hadrosaurs. So they've essentially dominated multiple predator roles within their ecosystem, and I think that's a very interesting ecological dynamic.
Question from Darren: what T-Rex specimens have been found in Mexico?
The specimens that I recall, there are a couple of isolated teeth, and there's been a couple of isolated teeth. There's a potential Tyrannosaur species called Laboconia, or Laboconia, that's not really well known anymore. I haven't. There's only one publication really on that. But T-Rex itself, I think that there are a few isolated teeth of T-Rex found that date from that late Maastrichtian age. And they are that really large conical, more so than any other Tyrannosaur species from North America. And it really only fits with T-Rex. But again, they are just teeth. So it's really difficult to say whether or not they truly are T-Rex or if they represent something else. I do know that there are T-Rex. There's a T-Rex dentary from New Mexico that I've personally seen that's very obviously T-Rex. And then there's a maxilla of a T-Rex that's been found in Texas as well. So those are two of the most southerly occurrences of T-Rex, two of the absolute most southerly occurrences of T-Rex. And then there are some teeth, I think, that have been found and that have been attributed to Tyrannosaurus Rex as well. But I haven't seen those teeth in myself, so I can't say for certain from my point of view. But trusting for what other people have written, there are some potential Tyrannosaurus Rex teeth in Mexico.
Question from Dan. Would the grooves have been present in the soft tissue of Thanatotherystes as grooves, like in the illustration, I guess the art probably that was done for Thanatos? And would Tyrannosaurus and Displetosaurus have had similar grooves in their soft tissue?
Yeah, so they might not have been like the exact like keeled scale kind of patterning like we had with the actual illustration. I did like the illustration because it did enunciate those kind of grooves and how those grooves kind of showed off that Thanatotherystes had those weird characteristics. But I think that the differences in that scale and those texturing, so you have like what is just kind of your general rugosity and things like Gorgosaurus. Then you have those deep grooves in Displetosaurus, and then the ridges in T-Rex, and then you have a mixture of the ridges and the deep grooves in Thanatotherystes. I think that it's showing that there's potentially some sort of different scaling or potentially some sort of soft tissue that's going on in the facial region that differentiates between Displetosaurus and T-Rex and Thanatotherystes. And I think Thanatotherystes potentially, because it has both the Displetosaurus and the T-Rex-like characteristics, but kind of does its own thing with both of them. It suggests that it would be kind of a halfway point between both of those different morphologies. We don't know what that soft tissue morphology would be yet. Again, mummy, but I think I think that's kind of what it might relate to, is some sort of soft tissue structure. So yeah.
There's just a few last questions that I'll read, and then we'll let you go for lunch.
Sounds good.
Okay, so a question about bite force. Have bite force tests in small tyrants like Susquityrannus been done? And how does the bite force compare with that of larger species?
I don't think that bite force estimates have been done for some of our smaller Tyrannosaurs yet. One of the things is that like bigger Tyrannosaurs are really popular. We know they have these really bone-crushing bites, so we're always asking how powerful were they, right? So it's a kind of a popularity thing there. But also there's an issue with some of our smaller Tyrannosaurs just not having really well, or some of our smaller Tyrannosaurs just aren't preserved all that well. And this is both a sampling issue because smaller animals oftentimes are less likely to get preserved than bigger animals in the fossil record. But also these smaller Tyrannosaurs are also coming a lot of times from places that aren't quite as that don't preserve fossils just as well overall as some of our later Cretaceous places like here in Alberta. And I think that Alberta's just kind of got an exceptional fossil record that we can really ask those questions in. But at the same time, some of our smaller places, some of our smaller Tyrannosaurs like Guanlong, some of our Prostratosaurs and Dialong, those sorts of things, we could potentially start to be doing some of those bite force estimates on those animals as well, just to kind of address those questions and maybe even start to look at the evolutionary sequence of bite forces as we start to move towards some of our larger Tyrannosaur species.
Cool. Just going through last questions. Question from Jordan. Did Tyrannosaurs change their diets as they grew up? How might the menu have changed?
Yeah, so going back to that slide that I was talking about with the ecology, the potential differences in ecology. So because juvenile Tyrannosaurs were these longer-legged and more lightly built animals, it might suggest that they were potentially preying on faster prey than maybe adults could actually go after. And they were probably quite fast, actually. Then as adults, they were really heavily built. They probably actually weren't running. They were, or at least in the technical sense of running where you have a point in your stride where both of your feet are off the ground. They were probably just fast walking, and so they probably weren't quite as fast as some of the juvenile tyrannosaurs. But I think it does suggest that there is an ecological dynamic where you have these juvenile tyrannosaurs preying on smaller and faster prey, potentially with our larger adults preying on those larger mega herbivores like ceratopsids and hadrosaurs.
Question from Ian. What question intrigues you most regarding tyrannosaurs, particularly in the context of their ecology or behavior?
There's one question that I can't bring up. It's a really interesting question that you will see in the future. But I think nesting behavior would be a really interesting one to address, or kind of the really early ontogenetic stages. And we've recently only really begun to address that in a paper by Greg Funston and others, where they talked about very small neonate juvenile tyrannosaur material. But we're still very much missing tyrannosaur nests, really good embryo material, or just very young tyrannosaurs. So I'm really interested in seeing kind of what the anatomy and the morphology is of those really, really small baby tyrannosaurs. And I'm hoping that, again, in the future, that we'll be able to address those questions more thoroughly. But that's kind of the big one for me, is like looking at that. And also looking at, I guess, less so on the ecology and ontogeny sort of and behavior aspects. But I'm really also interested in learning about the rise to those really large tyrannosaurs. So that transition from our really small to our really large apex predator type tyrannosaurs, so the evolution of them.
Okay, maybe two last questions, and then we'll let you go. Another one by Ian. What do you think about the idea of a hybridization between contemporary tyrannosaurs like Gorgosaurus and Displetosaurus?
It's always possible. It would be really difficult. Hybridization in nature is quite rare, but there are occurrences that it does happen. I know that there's mitochondrial DNA that suggests that lions and snow leopards actually hybridized multiple times in their evolutionary history. So it does happen in nature, and we do see it in like modern animals as well, with like whales and such. But it would have been a very rare event. As for if it's possible, there's really no way of knowing unless we were to be able to find some sort of weird hybrid. And if we were to find a weird hybrid, I don't know if we'd be able to even recognize it. It would probably be so bizarre, but it's always possible, I guess, is the answer to that.
Cool. One last question, a special request from our friend Bill Bloss. Said, can you talk a little bit about the differences between the various juvenile Gorgosaurus known from the park, as they were of similar age when they died?
Yeah, so there's there are some minor differences between the morphologies of these different tyrannosaur species, or these these very small tyrannosaur individuals. They primarily relate to the kind of the ontogenetic stage. So at what points are different features acquired through ontogeny? And this is one of the big features that changes with Tyrannosaur ontogeny is that increase in snout depth, or at least in the skull. One of the big changes is that increase in snout depth and the acquisition of features that were facilitating a much more robust skull, which would give greater bite force. So there is some variation that you can see in individuals that are of similar size, but it's generally not that much. But there are features that you can. But there are features that you can see that indicate that some of them individuals might have been a little bit younger or a little bit older than the others.
Well, I think we'll stop it there because I've been taking up a lot of your time. So I'd like to thank everyone for submitting questions. I apologize for those I didn't get to your questions. And I just want to say, Jared, we got lots of comments, people thanking you and saying it's an excellent talk. They really enjoyed your talk. It was very educational, so just wanted to pass it along. I didn't read all of them, but there were lots of them. So just like to thank you again for giving a great talk. And then and again thank everyone who watched for attending, submitting their questions. Invite you to come back again for next week's talk. And again, Jared, thank you very much, and good luck with the rest of your research. We're looking forward to seeing you come another talk after your next big discovery of a Tyrannosaur mummy. How about that?
Oh, you're not supposed to tell anybody about that one. We don't have it yet, just for everybody thinking. We're looking though. But yeah, so thanks for everybody for tuning into this talk, and thanks to the Royal Trail Museum Speaker Series for having me.
Okay, thanks. Good job.
All right,
See
have a great
ya.
one.